All right, looks like we are back in business. Sorry for those of you who were expecting a stream yesterday. I was a little under the weather and it just wasn't happening. That and also some bad timing and chores I had to take care of and whatnot. But that's behind us now. Let's just continue with calculus. My plan for today is to wrap things up, so whatever doesn't get covered, I guess doesn't get covered. But hopefully there was enough variety in the two previous streams and today's stream that I've helped with at least one thing that you might have been worried about. Anyway, where do I want to begin for today? So last time we left off with trig substitution. I guess today we're going to look at partial fractions. Let's start with partial fractions, and there's a reason why I covered trig substitution first. There are actually cases for partial fraction decomposition where trig substitution may be needed. Let's see. What do I want to start off with as an example? How about so many to choose from. Oh, I'm liking this one. So I think this is gonna have an irreducible quadratic factor. It's got x squared minus x plus 6 over x cubed plus 3x. Okay, how on earth do we integrate this? So you've done partial fraction decomposition before in pre-calculus. I would hope you remember the details of that. But anyway, if you don't remember, I think this will help jog your memory. So first we need to decompose this thing into partial fractions. Let's see. X squared minus x plus 6 over x cubed plus 3x. I'm going to factor an x out of that, leaving us with x squared plus 3, and x squared plus 3 cannot be factored any further. That's an irreducible quadratic. So I'm going to decompose this into, it looks like, two partial fractions. One I'm going to call a over x, plus another one I'm going to call bx plus c over x squared plus 3. It's not just b over x squared plus 3. If you have an irreducible quadratic factor, then for the numerator you want to actually have a linear function. And as for why that is, I could spend the time explaining it, but I already have in a video I recorded a few months ago for one of my students when I was, for whatever reason, unable to remember how to explain it on the spot, but after the lesson I recorded a video and sent it to him. But yeah, I'll post the link to that video after this stream is done. Maybe I should have put it in the description right from the get-go, but oh well, I forgot. You can wait 3 hours or so for me to post it in the recording, in the description, or maybe in the comments section. I don't know. Check both places and you'll find it eventually. Anyway, back to what we were doing. So we can decompose this into the sum of two fractions, and it looks like what I want to do next is multiply by x times x squared plus 3 on both sides of the equation. That will give us x squared minus x plus 6 equals a over x times x squared plus 3 is just going to give us a times x squared plus 3 plus, then we've got bx plus c over x squared plus 3. If you multiply it by all that stuff, x squared plus 3 cancels, and you're just left with x. Okay, and at this point, you could just plug in arbitrary values for x until you can find a, b, and c. So for example, I could plug in, let's say I plug in x equals 0, that would get rid of all this, and then you'd get a times 0 squared plus 3, so 3a is equal to 0 squared minus 0 plus 6, 3a equals 6, therefore a equals 2. So that's one way you could do it, and that's probably how most teachers have shown you how to do it. But you'll see in the video that I promise to link to after the stream is done, that there is another way of doing this, and that other way is actually better because it exposes the problem with not having a linear function in your numerator for irreducible quadratic denominators. And the other problem that's also highlighted in that video, as you'll see, is the problem of repeated factors, which we'll probably do a case of in this stream anyway. So I'm going to do it that other way. And maybe when we do the repeated factors thing, we'll highlight why we do things the way we do with repeated factors. I'm rambling too much. Let's just get on with this. So I'm going to distribute the a and distribute the x over here, and so we get ax squared plus 3a plus bx squared plus cx. And if I go ahead and combine like terms, ax squared plus bx squared is a plus b x squared, and then we've got just cx, and then we've got, for our constant term, just 3a is equal to x squared minus x plus 6. Okay, so here we see that a plus b has to be equal to 1. And we see that c has to be equal to -1, and we see that 3a has to be equal to 6. We see that 3a has to be equal to 6. Okay, since 3a has to be equal to 6, we know then that a must be 2. C has to be -1. And since a has to be 2 and a plus b has to be 1, that would mean that b has to be -1 because a is already 2. 2 plus -1 would give us 1. Okay, and that takes care of it. So if I didn't do bx plus c here, if I just did b, what would have happened? What would have happened if I just had b? I guess I'm already explaining what the linked video is supposed to explain anyway. Oh well. So if I just did b over x squared plus 3, then what I would have here, I wouldn't have the x or plus c here, which would mean I would have had, let's see, I would have had ax squared, and I would have had plus 3a, and then I would have just had this x, and this plus c wouldn't have been here, so it would have just been b times x. Or if you rearrange it, you would get ax squared plus bx plus 3a, and somehow that's supposed to equal x squared minus x plus 6, but you can see that this isn't going to work because 3a equaling 6 would require a to be equal to 2, but then that means you get a 2x squared here, and how on earth is 2x squared going to be equal to 1x squared? It doesn't work. And then that would mean b would have to be -1, which I guess isn't that big of a problem in comparison to a having to be 2. So yeah, it just doesn't work. It doesn't work with just b over x squared plus 3. It has to be bx plus c. You need 2 constants introduced for a quadratic denominator. Anyway, back to the problem at hand. So now that we know a, b, and c, we can go ahead and rewrite this. I just like writing these coefficients on the outside. Well, I can't really do that for this one. But for a over x, I'm going to write it as a times 1 over x. So 2 times 1 over x plus, let's see, bx plus c is just going to be negative x plus, well, minus 1. Actually, I'll factor out the negative. Since it's negative x minus 1, I can factor out the negative. Let me rewrite this on a new sheet of paper. I'm running out of space. What a way to start a stream. So we've got x squared minus x plus 6 over x cubed plus 3x is equal to, I'm going to write that as 2 times 1 over x, and then minus, it was going to become, after factoring out the negative 1, x plus 1 over x squared plus 3. Okay, does that match up with everything we had up there? Yep, I don't see any problems. Okay, and let's scribble that out. Okay, so that's what we are now integrating. So integral of this expression with respect to x is equal to the integral of this expression with respect to x. Okay, integral of 2 times 1 over x, that's easy enough. Integral of 1 over x is the natural log of x. So we've got 2 natural log of x. And I guess I should have absolute value bars here. Can't take the natural log of a negative. Okay, minus, this one is a bit more complex. So for this one, I'm going to integrate it as a separate integral. We've got x plus 1 over x squared plus 3 dx. What can we do about this? Well, in this case, I don't think we have to resort to completing the square and doing trig substitution. We might be able to do it with a simple u substitution. Let me see. If I do u equals x squared plus 3, du would be 2x dx. But how on earth am I going to get my 2x dx out of that? Well, okay. We can split it. Looks like we might have to do trig substitution in the end after all. We can split that integral into 2 parts because x plus 1 over x squared plus 3 is the same as x over x squared plus 3 plus 1 over x squared plus 3. Okay, and here we can make use of the u substitution, at least for this part. So multiply by 2 over 2. I'm just going to multiply a 1/2 on the outside. And now we've got a 2x dx, which becomes our du. And x squared plus 3 becomes u. So du over u integral of 1 over u du is just ln of u, so ln of x squared plus 3. So now we've got 2 ln of x minus 1/2 ln of x squared plus 3 plus the integral of 1 over x squared plus 3 dx. So you could use trig substitution here, or you could actually use u substitution if you remember the derivatives of your inverse trig functions. If you remember the derivatives of your inverse trig functions, you could actually just use regular u substitution here. So 1 over x squared plus 3. Let's see. We'll do an example later that definitely requires trig substitution, but for this one, if you remember that the integral of 1 over x squared plus 1 is equal to arctangent or inverse tangent of x plus c. If you remember this, then we can take advantage of it. We can rewrite x squared plus 3 as, let's see, if we divide everything by 3, then we can rewrite that, I guess I'll do it over here, 1 over x squared plus 3 is equal to 1 over, if I factor out a 3, we've got x squared over 3 plus 1. And then we can do a u substitution with u equals, let's see, the square root of x squared over 3 would be x over square root of 3, giving us du equals 1 over square root of 3 dx. And if we do that, then our integral becomes, maybe I shouldn't be writing this stuff over and over again each time. I probably should have just solved this separately, but oh well, poor planning on my part. Now you know what not to do on your exam in order to shave off minutes and seconds. Okay, so 1 over x squared plus 3. We pulled a 3 out of there, so I'm just going to have that factored out as a 1/3. And then, so we're going to pull that out as a 1/3, and then x squared over 3 plus 1. Well, x squared over 3 becomes u squared, so that's going to be u squared plus 1. And then to get our du is 1 over root 3 dx, so we have to multiply by root 3 over root 3. We have to multiply by root 3 over root 3, and that way we can take 1 over root 3 along with dx to form our du, and we'd have an extra factor of root 3 on the outside. And there we go. Okay, and this integrates to arctangent, so let's pull up a new sheet here. Which color should I go with? Let's go with red. And so we end up with 2 natural log of x minus 1/2 natural log of x squared plus 3 plus, I'm just going to write that as, well, root 3 over 3 reduces to 1 over root 3. And then that integrated to arctan of u, and u was equal to x over root 3, the way we defined it. and plus c. All done. There we go. So that's your integral of x squared minus x plus 6 over x cubed plus 3x. This is what it ultimately integrates to. All right, let's have a look at another one. Now let's look for an example with repeated roots. This one looks good. So it says integral of, it's the integral of, where did it go? X squared minus 5x plus 16 over, and they've already factored the denominator for us, how nice of them, 2x plus 1 times x minus 2 squared dx. All right, how do we decompose this thing? So we've got x squared minus 5x plus 16 over all that good stuff is equal to something over 2x plus 1 plus something over x minus 2 squared, but that's not the end of it. We also have to add plus something over x minus 2. Whenever you have repeated factors, you're going to need one term for each power of that factor. So if this was x minus 2 cubed, I would have had b over x minus 2 cubed plus c over x minus 2 squared plus d over x minus 2, and so on and so forth. Whatever the multiplicity of the repeated factor is, that's how many times you have to have that show up in your decomposition. That's how many partial fractions you need to include for it. And of course I'll just link the video and you'll see the reason why we have to do it for the case of repeated roots. I think in the video I gave a really simple and easy to understand example of what goes wrong when you don't do this. So I'll just leave it up to that video. Anyway, I'm going to multiply everything by 2x plus 1 times x minus 2 squared, and that leaves us with x squared minus 5x plus 16 equals a times x minus 2 squared plus b over x minus 2 squared times this stuff leaves us with b times 2x plus 1. And then c over x minus 2 multiplied by all this stuff is going to give us c times 2x plus 1 times x minus 2. All right. So in this case, I'm just going to use the standard method that most teachers will tell you to use instead of grouping terms like I did with the earlier example. So if I try x equals 2, then that would mean my a is eliminated. So when x equals 2, I would get 2 squared is 4 minus 5 times 2. 4 minus 10 is negative 6. And negative 6 plus 16 is 10. We would get 10 equals, that's going to be 0. And then plus b times 2 plus 1, so that's 5. And then this is going to be 0 because 2 minus 2 is 0. And so we get 5b equals 10, therefore b equals 2. All right, similar reasoning. If we do, let's try x equals, what would this have to be? -1/2. Let's try x equals -1/2. For x equals -1/2, we would get -1/2 squared is going to be 1/4 minus 5 times -1/2, so that's plus 5/2. 1/4 plus 5/2, so that's 1/4 plus 10/4, which is 11/4, and then 16 is 64/4. So, well, actually, wait, no, 11/4. I'll think of it as 2.75 plus 16 is 18.75. Okay, 18.75 on the left-hand side equals, if I plug in -1/2, then the b term is going to be 0 and the c term is going to be 0, and all I'll be left with is this. So a times -1/2 minus 2, that's -2.5. And -2.5 squared is positive 6.25. And then, yeah, plus b times that stuff is going to be 0, plus c times that stuff also going to be 0 when you plug -1/2 in for x. Okay, and 18.75 divided by 6.25, 18 over 6 is 3, and 75 over 25 is 3. So yeah, it looks like A is equal to 3. Okay, and now to find C. So with C, we don't have a really easy value for x that we can plug in to eliminate both A and B, unfortunately, but that's not too bad because we now know what A and B are supposed to be, so it's not bad news if the A and B stay. So at this point, we can just pick any x value that we haven't used before. Let's pick x equals 0. 0 is usually a good, easy choice to go with. So if I go with x equals 0, then what do we get? 0 squared minus 5 times 0 plus 16, which would be just 16, equals a times 0 minus 2 squared. Well, a is 3, and 0 minus 2 is -2, squared is 4, plus b we now know is 2. 2 times 0 plus 1 is 1, plus we've got c is currently unknown. 2 times 0 plus 1 is 1, times 0 minus 2 is -2. Okay, 3 times 4 is 12, plus 2 times 1, so that's 14. Subtract 14 on both sides. 16 minus 14 gives us 2, equals, all that's left on the right-hand side would be -2c. Therefore, c must be -1. And there we go. All right, so it looks like we are integrating uh, 3 over 2x plus 1. So 3 times 1 over 2x plus 1. Plus, we've got b equals 2, so I'm going to write that as 2 times 1 over x minus 2 squared. Plus, well, I guess in this case, minus 1 times 1 over x minus 2 dx. All right, let's go ahead and solve that on a separate sheet. So 3 times 1 over 2x plus 1. So there's two different ways you could go about this. You could do u substitution with u equals 2x plus 1, or you could factor a 2 out of the denominator, and then you'd get a really simple integral. But of course, if you've done problems like this enough times, you should realize the pattern by now. It's going to be natural log of 2x plus 1 divided by 2, the coefficient of the x. So we should be getting 3 natural log of 2x plus 1 all over 2. So that's 3/2 natural log of 2x plus 1 plus, let's see, 2 times 1 over x minus 2 squared. Again, you could do u substitution here. U equals x minus 2. You'd have 1 over u squared, which is u to the negative 2, integrates to u to the negative 1 over negative 1, and in that case your du would be the same as dx. But of course, if you've seen it enough times, you should be able to just mentally sort through all that. So let's see, not plus, it's going to be minus 2 times 1 over x minus 2 to the first power. And then minus 1 over x minus 2, that should be simple. That's minus natural log of x minus 2. And of course, don't forget your constant of integration. And there we go, and this marker's pretty much dead. Alright, time to replace it. That goes to the trash, and let's see what we can pick. What's a good color to replace? I guess that would have been called seafoam green if I'm not mistaken. What would be a good color to replace it? I already have a shade of that color. I guess we can pick one of these other greens. Okay, let's go with this lime green color. That should be good. Let's put those away. I need to make my desk design more ergonomic, but that's a problem for another day, I suppose. Let's see. I want one where we actually have to complete the square and trig substitution. Where can I find one of those? The problem is, I don't think there is an easy way to just look at a problem and know whether or not it's going to end up being that way. Well, actually, there is a way. It would have to be an irreducible quadratic factor that actually has 3 terms instead of 2. If I can't find one in here, then I can make one up. That's probably what I'm going to end up doing, isn't it? Let me think. So I want something where b squared minus 4ac is negative. That shouldn't be too hard to put together. How about, and I'll just make one up. I'll make my own. Fingers crossed, hoping it doesn't become some ridiculously hard problem, as is often the case when I try to make up my own problems without thinking them through. Let's do... Let's throw in an x minus 2 in there just for the fun of it. And also we're going to have x squared plus 4x plus, let me think here. What do I want this to be? So it would be looks like anything greater than 4 would actually work. Okay, let's go for 18. I think that should do it. B squared minus 4ac. Oh yeah, that'll work. That'll work just fine. Okay, and in the numerator, let's put in, oh, I don't know, how about x squared plus 2x minus 9. Okay, and let's integrate that. Oh, and of course it's integrated with respect to x. Definitely don't forget the dx there. Okay, so let's try and decompose this. X squared plus 2x minus 9 over x minus 2 times x squared plus 4x plus 18. Let's see what we can do with this. So we're going to have an a over x minus 2, and then we're going to have a bx plus c over x squared plus 4x plus 18. All right, multiply the denominator over to both sides. Something tells me we're going to get very nasty fractional values for a, b, and c. X squared plus 2x minus 9 is equal to a times x squared plus 4x plus 18 plus bx plus c times x minus 2. All right, let's try plugging in a bunch of different x's until we can solve for a, b, and c. If I plug in x equals 2, then I should be able to solve for a. Plugging in x equals 2 would make x minus 2 0, which gets rid of all that, leaving us with, let's see, so 2 squared plus 2 times 2, so that's 4 plus 4 minus 9 is negative 1 equals a times 2 squared is 4 plus 4 times 2 is 8, so 8 and 4, that's 12, plus 18 is 30. Oh my goodness, and that gives us a equals negative 1/30. So that gives us a equals negative 1/30. There's our first not so fun fraction. Then we can try, I guess x equals 0 would eliminate b, so let's go for that. If I try x equals 0, then, well, 0 squared plus 2 times 0 minus 9 is negative 9 equals a times, that's 0, that's 18, so I guess, well, since we know it's negative 1/30, negative 1/30 times 18 is negative 18/30, or I guess we can factor out a 6 from there. We get negative 9 equals negative 3/5, negative 3/5, plus the other stuff. So plus b times 0 is just 0, plus c times 0 minus 2. So negative 2c, in other words, plus c times negative 2 plus c times negative 2. Okay, add 3/5 to both sides. So negative 9 is the same as negative 45 over 5, plus 3 over 5 is negative 42 over 5, equals negative 2c, which means that dividing by 2, 42 over 2 is 21, so it looks like c is going to be 21 over 5. c equals 21/5. And to solve for b, let's try plugging in 1. 1 should be simple enough to work with. So if I plug in 1 for x, then 1 squared plus 2 times 1, so that totals to 3, minus 9 is negative 6, equals a times 1 plus 4 times 1, so that's 5 plus 18 is 23. That doesn't look very pleasant to deal with, times a itself, which is negative 1 over 30. Oh no. Oh no, this doesn't look pleasant at all. Plus b times 1 is, of course, just b, plus c, which we now know is 21/5, times 1 minus 2, so that's just negative 1. I guess I'll write it in there, times negative 1. Okay, yeah, this doesn't look like it's going to be too pleasant. So we've got, I guess I'll write it further to the left, negative 6 equals, we've got negative 23 over 30, which doesn't simplify at all. And then if I distribute the negative 1, that's going to be minus b, and also minus 21 over 5. Let's multiply everything by 30 to clear the fractions. That would give us negative 180 equals negative 23 minus 30b minus, let's see, 21/5 times 30. 30 and 5 reduced to 6. 21 times 6 is 126. Add 126 to both sides. So 180 minus 130 would be 50, and then give back 4, that's 54. Yeah, negative 154 it looks like, equals negative 23 minus 30b, and add 23, that gives us negative 131 equals negative 30b, and divide by negative 30, that cancels out the negatives. 131 over 30, that is b. b equals 131 over 30. See, this is what happens when I try to come up with my own problems on the spot. This is what always happens when you don't have time to think about what kind of problem you're designing and what you want the numbers to be. You get very clunky numbers to work with, but it's still doable. It's still solvable. Let's go ahead and see where we can go from here now. So I guess we'll rewrite our integral as the integral of let's see, negative 1/30 times 1 over x minus 2, negative 1/30 times 1 over x minus 2, plus, there's no way out of this one, 131 over 30x plus 21/5. 131 over 30 x plus 21 fifths over x squared plus 4x plus 18 over x squared plus 4x plus 18 dx. Well, we already know how to integrate this part. It's just going to be negative 1/30th natural log of x minus 2. Negative 1/30th natural log of x minus 2 plus the integral of the remaining stuff. Do I want to split this into two separate fractions? Yeah, I think I might actually want to do that. So it's plus 1/31/30ths of x over x squared plus 4x plus 18 plus 21 fifths times 1 over x squared plus 4x plus 18. Okay, and of course we can move these fractions outside of the integral and get them out of the way. So I guess I'll do that right now. So 1/31/30 outside there and 21 fifths out here. All right, where to go from here? Where to go from here? So here you definitely have to do trig substitution. First we have to complete the square. So we've got x squared plus 4x plus 18. How do we complete the square on that one? So half of 4 is 2, and then 2 squared is 4. So it looks like x squared plus 4x plus 4 is a perfect square. It's equal to x plus 2 squared. Okay, x squared plus 4x plus 18 then is the same as x squared plus 4x plus 4, except it's 14 more. So x squared plus 4x plus 18 equals x squared plus 4x plus 4 plus 14 equals x plus 2 squared plus 14. That's effectively what we have. Okay, so let's integrate this part first. Integral of x over x plus 2 squared plus 14 dx. So we would want to use trig substitution here. Well, would U substitution work? No, I don't see it working. Yeah, trig substitution is inevitable. It's unavoidable here. Unless you do something really, really clever with your algebra, which I'm blanking on right now, but I remember one of my professors had a little trick to make this a whole lot easier. I just don't remember what the trick was. Anyway, in this case it looks like I've got a sum, so I want this to become tangent squared plus 1 equals secant squared, and in order to do that I need to divide or factor out a 14 from the denominator. So that's going to be 1/14th integral of x over x plus 2 squared over 14 plus 1 dx. Okay, so that means x plus 2 squared over 14. I want that to be my tangent squared of theta. And so tan of theta is equal to x plus 2 over the square root of 14. Multiply by square root of 14 on both sides and subtract the 2. You get x equals root 14 tan theta minus 2. And dx is equal to root 14 secant squared of theta d theta. Alright, so that is our first step towards solving this. Let's see, so that gives us, so this becomes, I'll start it over here to the left so I don't waste any real estate. We'd have our integral is 1/14th integral of x gets replaced with root 14 tan theta minus 2. Root 14 tan of theta minus 2. And then x plus 2 squared over 14 becomes tan squared of theta plus 1. And then our dx becomes root 14 secant squared of theta d theta. Let's see, and tan squared plus 1 is equal to secant squared, so this cancels out with this. And now we are left with, if I distribute the root 14, then we're left with 1/14th integral of root 14 times root 14 is 14 tan of theta minus 2 root 14, which is just a constant, integrated with respect to theta. Okay, and from here you might remember that the integral of tan theta is the natural log of, well, the negative natural log of cosine theta. Is that right? Derivative of natural log of cosine theta is 1 over cosine times negative sine, and then the negative on the outside makes it positive. Yeah. And yeah, the 1/14th and the 14 will cancel out, so we've got negative natural log of cosine of theta minus 2 root 14 times theta. And draw yourself a reference triangle. Let's see, how do we define theta? Well, tan of theta is x plus 2 over root 14, so opposite over adjacent should be x plus 2 over root 14, which means the hypotenuse is x plus 2 squared plus root 14 squared, so that's x plus 2 squared plus 14. And there we go. So I guess continuing on another sheet. Well, actually no, I have some space right up there that I can make use of. Got a little bit of space here that we can take advantage of. Before I forget. Actually, do I want to? No, the plus c will come in later for our final integral. We're only, I guess, 2/3 of the way through this. So we get negative natural log of, what's cosine theta? Cosine theta is adjacent over hypotenuse is root 14 over x plus 2 squared plus 14. I guess I don't really need the absolute value symbol here then, because x plus 2 squared, anything squared, is going to be positive, except 0 squared, of course. And a positive plus 14 is still positive, and root 14 over that is still positive. So yeah, you don't actually need the absolute value symbol. anymore. And then minus 2 root 14 times theta. So that's minus 2 root 14 times theta. We would just define it as inverse tangent of x plus 2 over 14. Tan inverse or arctangent, however you prefer to write it, of x plus 2 over root 14. And there we go. That takes care of the middle integral. Just take that whole expression times 131 over 30. And that's your middle integral. And you'll have to do similar stuff to solve that third integral. And then all of that plus c. And there you go. That would solve your problem. I'm not going to continue the rest of it. I think I showed the crucial part that I wanted to show. But yeah, that's how it goes down. For a 45-minute exam, I don't think they would give you something that would be this time consuming, but maybe they'll give you simpler numbers and fractions that are not as nasty as mine. Let's see, where do I want to go from here? I guess we can do integration by parts. Wait, where is integration by parts in this book? Did I skip over it? Oh, it was before trigonometric integrals. Interesting. So with integration by parts, I'll show a basic problem and then I guess what I like to call a looping problem, 2 cases of what I like to call looping problems. So we've got, for example, integrate the following. Find the integral of x cosine of 5x dx. Pretty simple to do. Some teachers will just have you memorize the formula. Integral of u dv equals uv minus integral v du. Other teachers will have you use a table, and I like using the table. It makes it easier to just organize your information. So on one side is the part that I'm going to differentiate, and on the other side is the stuff I'm going to integrate. So in other words, here is where my u goes, and here is where my dv goes, and then once you integrate the dv, that'll give you your v, and if I differentiate my u, that'll give me my du. So that's how that table works in case you're one of those students who hasn't seen it before. So, choices for you. As a general strategy, I'm not going to promise that this will work 100% of the time, but as a general strategy, you want to go down the following order when deciding what to choose for u. Logarithms, inverse trig functions, algebraic expressions, so polynomials and other power functions, even if it's not necessarily a polynomial, if it's your variables raised to constant powers, even if they're in the form of square roots or fractional, or, well, negative or fractional exponents. Any sort of power function, that would go next. Then trig, then exponential. So the further to the left it is, the better of a choice for you it will be most of the time. I can't guarantee it works all the time, but that's usually where you want to go. The idea is that you want to choose something for you that will become simpler after you differentiate it. You want to choose something that gets simpler when you differentiate it, not something that gets more complex. Anyway, in this case, our choice for u is going to be x. because differentiating x simplifies it to a 1. And our dv then is just going to be cosine of 5x dx. I usually don't write the dx, but you can imagine that it's there. Integrating cosine of 5x gives us 1/5 sine of 5x. Okay, so our uv is just multiply across the diagonal of this table, multiply here, and we've got x times 1/5, so 1/5 x sine of 5x, that's going to be our uv, minus the integral of v du, minus the integral of v times du. So you integrate the product of that row. So minus, while multiplying by 1 doesn't change anything, so that's 1/5 sine of 5x inside of our integral dx. And that ought to do it. So integrating sine of 5x is going to give us negative cosine of 5x over 5. So we get 1/5 x sine 5x. And then the negative from integrating sine is going to cancel with the negative we have outside, so that becomes plus 1/5, well, actually 1/25, because integrating sine of 5x is going to have us dividing by 5. So plus 1/25 cosine of 5x plus c. And of course, you can always check if you did it right by differentiating. You'd have to do a product rule there, but that shouldn't be too troublesome. And there we go. So that's a very simple classic example. Now, the table method actually helps you, quickly set up cases where you would have to apply integration by parts repeatedly. So, for example, if this had been, let's say, x cubed cosine of x. Yeah, I'll just make it a little bit simpler. If we had something like x cubed cosine of x dx, then setting it up as a table actually makes it a whole lot simpler, because you would go, okay, here's my x cubed, here's my cosine of x. Integrating cosine gives us sine. Differentiating x cubed gives us 3x squared. And so you'd have x cubed times sine of x minus the integral of 3x squared times sine of x. Well, that's another integration by parts. And I would choose 3x squared for my next u, and I would use sine of x dx as my next dv, and repeat the process all over again. So we would have, let's see, 3x squared becomes 6x, and then integrating sine of x gives negative cosine of x, and that would give us 3x, well, negative 3x squared cosine of x minus 6x cosine of x, or minus the integral of 6x cosine of x, and that integral is yet again an integration by parts. Set 6x for your newest u, and negative cosine x dx for your newest dv, and repeat the process again. Whoops, was I about to write x there? No, 6, and then integral of negative cosine is negative sine. And if you follow the negatives that are produced at each step when you do this integration by parts, then it shouldn't be too hard to see why you get positive x cubed sine of x followed by the negative of 3x squared times negative cosine of x, followed by the positive of 6x times negative sine of x, followed by the negative of the integral of 6 times negative sine of x. So you just, every other multiplication you do, you multiply by a -1. If you expand it out and write it, it's not too hard to see why that's the case. If I called this, I don't know, if I called this u0 and I called this u1 and u2 and u3, and then I guess that would make this, well, this was dv0, so I guess that would make this v0, which is also the same as dv1, so this would be v1, and this would be v2, I guess. Did I do that right? Well, actually, no. This wouldn't be u3. This would be du3. But yeah, if you just did it the old-fashioned way without the table, your first integral of u dv, well, you'd have integral of u0 dv0 gives you u0 v0 minus the integral of v0 times I guess du1 is what we would call it. But that itself is going to become, let's see, u0 v0 minus the integral of v0 du1 is going to become u1 times v1 minus the integral of v1 times du2. And if you distribute that negative sign, I think you can see where the alternating signs keep coming from. The next layer in, you would have a negative sign to distribute over whatever this turns into, and that's why the signs keep alternating. If that's too confusing and it's throwing you for a loop, don't worry, it's not the most crucial thing to know, though I would recommend after the AP exam you come back to this and try thinking about it, because at the end of the day, the most important thing is not to just pass the exam, but to actually learn calculus and understand it. Anyway, let's go ahead and work this out. So this is just going to become x cubed times sine of x. And then we've got plus the negative of 3x squared times negative cosine of x. That would be negative 3x squared cosine of x times a negative is plus 3x squared cosine x. And then times the positive of 6x times negative sine x. 6x times negative sine x is negative 6x sine x. And multiplied by positive 1 doesn't change it. And then finally, we've got minus the integral of 6 times negative sine x. 6 times negative sine x is negative 6 sine x times a negative is a positive integral of 6 sine of x dx. And if we integrate that, that's pretty easy. It's just going to be negative 6 cosine of x plus c. So equals x cubed sine of x plus 3x squared cosine of x minus 6x sine of x and then that's going to become minus 6 cosine of x plus c. All right, and that's all to show the advantage of using the table. Now then, looping problems, as I like to call them. How about this one? So it says e to the 2 theta sine of 3 theta d theta. Integral of e to the 2 theta, well, I'm just going to make it x because it's easier to write. E to the 2x times sine of, what was it, 3x? Yeah, sine of 3x dx. All right. Let's see what we can do here. So in this case, no matter what you pick for u and what you pick for dv, you've got two functions that are going to integrate and differentiate forever. You can differentiate e to the 2x or integrate it forever. It's never going to reduce down to 0 or something simpler. It's always going to be something times e to the 2x, whether you integrate it or differentiate it. So you're not gaining any ground by doing either of those operations on e to the 2x, and a similar story can be said for sine. For sines and cosines, you can integrate and differentiate them forever. So in a case like this, what you're really looking for is the moment where this thing loops, and it'll make more sense once you see it if you haven't seen it before, and if you haven't seen it before, what is your teacher doing? Unless you're self-teaching, in which case, well, I mean, if you're self-teaching, I would expect you to be responsible enough to thoroughly comb through the textbook or whatever learning resource you're using. So maybe for those who self-teach, there's a little bit more blame for them to take on for not knowing about this, for not having seen it before. But anyway, this is review, so maybe you've seen it and forgotten it. Let's do... I think I'll have an easier time differentiating the trig function and exponentiating, or integrating rather, the exponential function. But that's just my preference. You could swap these and you'd be fine. It doesn't really matter in the end. So integrating e to the 2x gives me 1/2 e to the 2x. Differentiating sine of 3x gives me 3 cosine of 3x. I'm going to do this again, and integrating again gives me 1/2 is 1/4 e to the 2x, and 3 times 3 gives me 9, negative 9 sine of 3x. And at this point I can stop, because at this point I have found a loop. So if I write it out, what I have is, let's see, plus, minus, plus. So what I have is e to the 2x sine of 3x is equal to, I guess I'll write it down here so that I have a lot of space, e to the 2x sine of 3x dx is equal to 1/2 e to the 2x sine of 3x minus, and then it's 1/4 times 3, so minus 3/4 e to the 2x cosine of 3x, and then it's going to be plus the integral of that stuff, so plus the integral of, it looks like negative 9/4, so that's minus 9/4 the integral of e to the 2x sine of 3x dx. Wait a minute. That's the same thing we started with. That's the same thing we started with. This is the same as this. We've gone around in a circle. We've completed a loop. Okay, this is actually good news. We can actually take advantage of this to find the solution, because since these integrands are the same, I can just add these. I can add this over to the left-hand side, just like I would do with any algebraic expression, right? If this was x equals a bunch of stuff and then minus 9/4 x, you would just add 9/4 x to both sides and solve for x. Well, same business here. So if I add 9/4 of this integral over to the left-hand side, 1 of this integral plus 9/4, so I guess I'll write 4/4 plus 9/4 is 13/4. So 13/4 integral of e to the 2x sine of 3x dx equals 1/2 e to the 2x sine of 3x. Wait, what did I do? Sine of 3x minus 3/4 e to the 2x cosine of 3x. And I guess there would have to be a plus c out there somewhere. But multiply by 4/13. Multiply by 4/13, and we get, as our final integral, we get integral of e to the 2x sine of 3x dx equals, multiplying by 4/13, 4/2 is 2, so that's going to be 2/13 e to the 2x sine of 3x minus, let's see, 4/13 times 3/4. Well, 4/4 would cancel out, and you'd be left with 3/13 e to the 2x cosine of 3x. And of course, there's a plus c, since this is an indefinite integral. And there we go. So that takes care of a looping integral. Let's take a look at one other example of a loop. So let's do integral of, let's say, sine of 2x times cosine of 5x dx. So if you know a certain trig identity, you could actually simplify this and not have to use integration by parts at all, but memorizing that trig identity is probably not worth it, since it's very rarely used outside of the context of this problem, and because you already have an alternative method for solving this problem. So it's not worth it in my book. If the relevant trig identity, or actually it's a set of trig identities, if those trig identities were used more often, then it would be more justifiable to commit them to memory, but I don't think that this one narrow circumstance justifies it. So yeah, we can just solve this using a loop in our table. Doesn't matter which one you pick, but I'm going to pick sine of 2x for differentiation and cosine of 5x for integration, just because it'll minimize the number of negatives I encounter. A derivative of sine of 2x is 2 times positive cosine of 2x, and then integral of cosine of 5x is going to be 1/5 positive sine of 5x. And then for one more step, in order to close my loop, because I need something involving sine 2x and cosine 5x, differentiate again, and we've got, let's see, that's going to be negative 4 sine of 2x. We multiplied by another 2. That's just the chain rule at play. And then integrating 1/5 sine, that's going to be negative 1/25 of cosine 5x. Let's see, positive, negative, positive. So we've got the positive product of sine 2x and 1/5 sine 5x. Let me write it down here again so that I have enough space. Integral of sine 2x cosine 5x dx is equal to, we've got 1/5 sine 2x sine 5x, and then minus the product of 2 cosine 2x and negative 1/25. Well, a minus and a negative is going to become a positive, so that's plus 2/25 cosine 2x cosine 5x. And then it's going to be plus the integral of this product. Negative 1/25 times negative 4 is positive 4/25. And then integral of sine 2x cosine 5x, which is exactly what we started with. Sine 2x cosine 5x dx. Okay, so subtracting 4/25 sine of 2x cosine of 5x on both sides, I guess I'll write this as 25 over 25. 25/25 minus 4/25 is 21/25 of the integral of sine 2x cosine 5x dx equals 1/5 sine of 2x sine of 5x plus 2/25 cosine 2x cosine 5x. Yeah, well, I guess it might be worth it to commit the product to sum and sum to product identities to memory, because it would go a whole lot faster, but I don't know. Considering how rare this situation is, it's probably still not worth it. Anyway, multiplying by 25 over 21 on both sides. So canceling 25 over 21 there, and we'd get integral of sine 2x cosine 5x dx is equal to multiplying by 25 and dividing by 21. So 25 over 5 is 5 over 21 sine 2x sine 5x plus multiplying by 25 over 21, 25 over 25 cancels, and we're left with 2 over 21 cosine 2x cosine 5x, and of course plus c. And there we go. So that's another classic case where you would want to make use of a loop. Okay, and I trust that you know how to deal with cases like the integral of arctangent of x or natural log of x. But if you don't remember how to do those, I would recommend looking them up. All right, so that takes care of integration techniques. Let's move on to arc length and surface area. You're going to hear me say the same thing I said about volumes in, was it the previous stream? Yeah, it must have been the previous stream. It couldn't have been the first one. Volumes is one of those mid-year topics. You're going to hear me say the same thing I said in the previous stream. If you understand the geometry, you don't need to memorize formulas. Where is my arc length section? Let me see. Okay, there it is. What should we grab as an example problem? So here it says find the exact length of curve. We've got y equals 1 plus 6x to the 3/2. And it's between 0 and 1, for x between 0 and 1. Okay, so if I were to draw a curve, so in this case 1 plus 6x to the 3/2, what would that look like? Okay, I think I can kind of see what it would look like. So it would look something like, if I'm not mistaken, it would look something like this. Okay, so we want to figure out the length of curve from 0 to 1. So I guess from 0, 1 to 1, 7, it looks like is what it would be. Yeah, this is definitely not to scale, but that's 1, 7. Okay, and what's the reasoning behind the formula for the length of curve? It's actually quite simple. If you zoom in on any piece of a curve that you're trying to measure the length of, let's say I zoom in on this piece, for example, and expand it outward, then we are looking at something that the more you zoom in on it, the flatter it looks. If you zoom in on this, eventually it starts to look a little flat. It's still curved, but looks flat if you zoom in on it sufficiently. If you take a small enough piece, it'll look flat. And if you have trouble seeing that, consider the fact that the Earth feels like it ought to be flat, but it's not. You know that the Earth is round. The reason it looks flat to you is because you're looking at a really, really, really tiny piece of it, which doesn't show enough of a sharp curvature for you to realize that it's curved. Anyway, in that case, we could treat this as being straight, as having a length which we would just call ds, a small change in length of the arc. And ds is related to a small change in x and a small change in y. So maybe I should draw a bigger picture of this. So yeah, I'll just draw something here. So ds, a small change in arc length, which is approximately straight, is going to be related to a small change in x and a small change in y. Pythagorean theorem, dx squared plus dy squared equals ds squared. And so from here, well, yeah, from here you can say that ds, a small piece of arc length, is going to be equal to the square root of dx squared plus dy squared, and from that point you can do whatever it is you need to do depending on the circumstances you're given. You can either factor out a dx squared or factor out a dy squared. So either you get ds is equal to square root of, if I factor out dx squared, then I'm left with 1 plus dy squared over dx squared times dx squared inside the square root, or if you pull it out of the square root, you get ds equals square root of 1 plus dy squared over dx squared. I'll just write as dy dx all squared. And then the dx squared that I pull out of the square root is just going to be dx. So either you get this, or you get the reverse situation. If you factor out the dy squared, it would be 1 plus dx dy squared times dy outside the square root. So those are the two possibilities that you can get. ds can also be equal to the square root of 1 plus dx dy squared dy. So those are the two possibilities that you can get. And yeah, I don't think it's that hard to remember. I don't think it's too hard to reconstruct this. It might seem like a long derivation at first, but if you do it a couple times, you'll see yourself mentally going through it in probably less than, I'd say, 30 seconds. If you do it enough times, you do just kind of start mentally jumping through the steps. Anyway, let's go ahead and apply this to this situation. So here we have, it looks like we're integrating with respect to x because they gave us the what do you call them? The lower and upper bounds in terms of x. That appears to be the case, but if you wanted to do this in terms of y, y goes from, let's see, it's 0, 1 to 1, 7, so you could integrate with respect to y from 1 to 7 instead. But of course then you would have to rewrite this equation and solve it for x. So integral of a bunch of pieces of arc length. The integral of a bunch of pieces of arc length gives you your total arc length. I guess we'll call that L. Or no, we can just call it S. It makes sense for the integral of ds to be called S. Anyway, integral from 0 to 1 of ds, ds being the square root of 1 plus, if we're integrating with respect to x, then we want dy dx squared. Okay, what is dy dx? Differentiating y with respect to x, we would get derivative of 1 is 1, derivative of 6x to the 3 halves is going to be 6 times 3 halves, that's 18 over 2 is 9, so dy dx equals 9, and then x to the 3 halves minus 1, 3 halves minus 1 is 1/2, so that's x to the 1/2. or in other words, 9 square root of x. And that's dy dx. dy dx squared is going to be 9 times 9, and square root x times square root x is 81x dx. Okay, and this is nice because I can do a simple u substitution here. I can do u equals 1 plus 81x du equals 81 dx. And I can multiply and divide by 81 here. So times 81 over 81 gives you the 81 dx you need to create your du. Integral from 0 to 1. I'll pull that 1 over 81 outside. That's going to be the square root of u, or u to the 1/2, and then 81 dx becomes du. And from here, the rest is history. It's 1 over 81 times u to the 3/2. So that's 1 plus 81x to the 3/2 evaluated from 0 to 1, which is 1 over 81 times, let's see, well, the 1 is gonna cancel out. Wait, is it? No. I'm forgetting it's in the parentheses. Okay, so plugging in 1, we get 1 plus 81 is 82 to the 3/2. Minus plugging in 0, we get 1 plus 0 is 1 to the 3/2 is 1. Okay, and then whatever that is, if it's a non-calculator question, then you can just leave it like that. If it is a calculator question, then plug it in. There's no way you're doing the rest by hand. And there we go. That's arc length. So maybe we should look at a case where we're integrating in terms of y. How about... Well, this one is marked in red, so supposedly it's going to be a challenge. Let me do it on a fresh new sheet. So it says y equals natural log of secant of x. Wait, but that's not in terms of y. Do we still want to do it then? Fine, why not? Let's do it. And then maybe we'll do another example for integrating in terms of y. It's not too different from doing it in terms of x, except that, you just need to get used to the relabeling. You're so used to doing dy dx that when you have to do dx dy, that kind of switching of the roles of the variables can confuse a lot of people. It just takes some getting used to. But yeah, let's see what we can do with this. So if I just follow the formula, if we integrate from 0 to pi over 4, it would be the square root of 1 plus dy dx squared dx. And dy dx is going to be what? Natural log of secant, so that's going to be 1 over secant of x times, by the chain rule, derivative of secant is secant tangent. Okay, that doesn't seem too bad. Secant of x cancels with secant of x. And we've got tangent of x. Oh, interesting. So, oh, of course it's the same as, okay, because earlier I think we did an integral of tangent of x, and I said it was equal to negative natural log of cosine x plus c. Yeah, this is an equivalent expression because the rules of logarithms say you can move the negative into the exponent, and cosine of x raised to the negative 1, that's 1 over cosine of x, which is secant. Okay, interesting. Didn't realize that, at least not immediately. Okay, then back to where we were going with this. So dy dx is tan of x, which means dy dx squared is tan squared of x. Ah. And then 1 plus tan squared of x, if you know your trig identities, that's going to be secant squared of x, and the square root of secant squared is just secant. And so the integral from 0 to pi over 4 of secant of x dx is what we have. And if you remember how to integrate secant, then you should be good to go. The trick is to multiply by secant plus tangent over secant plus tangent, and that will give you the result of natural log of secant plus tangent. And we're going to evaluate that from 0 to pi over 4. I mean, the rest is really just a matter of plugging things in, but let's do that real quick. So we would have the natural log of, if I plug in pi over 4, secant of pi over 4. So 1 over cosine pi over 4, 1 over root 2 over 2 is 2 over root 2, which is root 2. Try saying that 10 times fast. Plus tan of pi over 4, that's just going to be 1, minus natural log of secant of 0 is 1 over cosine of 0, which is 1 over 1, plus tan of 0 is 0. And of course, the rules of logarithms say that difference between logs is the log of the quotient, so this can be reduced to the natural log of, I guess I don't really need the absolute value bars anymore, root 2 plus 1 over 1 plus 0. Oh, actually, even without that, natural log of 1 is 0, so yeah, it's equal to the natural log of root 2 plus 1. Since that's already positive, I don't need the absolute value bars. Okay, now let's look for one where we actually integrate in terms of y. How about how about this one, which says, and I'll do it on a new sheet. How about this one, which says x equals y to the 4th over 8 plus 1 over 4y squared. And then that's from y equals 1 to y equals 2. Okay, so it's integral from 1 to 2 of the square root of 1 plus dx dy squared dy. And what is dx dy squared? So dx dy is going to be, let's see, derivative of 1/8 y to the fourth is 4/8 y to the third, or in other words, 1/2 y to the third, plus, let's see, so that's 1, I'll write it as 1/4 1 over y squared. 1 over y squared is the same as y to the negative 2. Derivative of y to the negative 2 is negative 2 y to the negative 3. Or, in other words, 1 over y cubed. So dx dy is 1/2 y cubed, and then negative 2 over 4, so that's minus 1/2 1 over y cubed. I wonder if I can simplify this more. So that's going to be, if I can factor out the 1/2, then we've got y cubed minus 1 over y cubed. I guess I could factor this as a difference of cubes, if I really wanted to, but do I want to? Not sure yet, but we'll see what pops up when we carry on with this. So that's dx dy. Dx dy squared is equal to the square of 1/2 is 1/4, and then the square of y cubed minus 1 over y cubed is y cubed squared, which is y to the 6th, minus 2 times y cubed times 1 over y cubed, so that's minus 2 times 1, plus 1 over y cubed to the 6th. Or no, 1 over y cubed squared, which is 1 over y to the 6th, is what I meant to say. Okay. And is that a perfect square? I think it might be. I think that might be a perfect square. Because, wait, of course it's a perfect square. What am I saying? Because I squared, I don't know what I'm saying. Let's just leave that as is for now. Oh, and I think I see where it's going. I think it's going to simplify to a different perfect square. Okay, so it's going to be 1 plus 1/4 of, I'll just write it as y cubed minus 1 over y cubed squared for now. And let's see, what is 1 plus that? So 1 plus, so that's going to be 4/4. 4/4 plus, if I distribute the 1/4 there, then we're going to have 1/4 y to the 6 minus 2/4 plus 1/4 1 over y to the 6th. And 4/4 combines with negative 2/4 to form positive 2/4. So that gives us 1/4 y to the 6 plus 2 over 4 plus 1/4 1 over y to the 6. And if you factor out the 1/4 again, then you would get, and is that visible on the screen? Okay. You would get 1/4 y to the 6 plus 2 plus 1 over y to the 6, which is a perfect square. You can say this is equal to 1/4 times y cubed plus 1 over y cubed squared. Okay, there we go. So our integrand simplifies. We get 1 over, or integral from 1 to 2 of the square root of 1/4 y cubed plus 1 over y cubed squared dy. And square root of 1/4 is a half. Square root of that stuff squared just cancels out with the square. And so you've got integral from 1 to 2. A little bit too much blue here. Integral from 1 to 2 of square root of 1/4 is a half. I'll factor that out. And then square root of that stuff squared is just that stuff unsquared. Okay, and now it's a rather simple integral. So we just take, let's see, 1/2 times, that's going to be 1/4 y to the 4th, and then 1 over y cubed is y to the -3, which becomes y to the -2 over -2, so that's -1/2 y to the -2, or -1/2 1 over y squared. In other words, evaluated from 1 to 2. And so we've got 1/2 times 1/4 of 2 to the 4th minus 1 to the 4th minus 1/2 of 1 over 2 squared minus 1 over 1 squared. Let's see, 16 minus 1 is 15. Might as well fully solve it since we're at the home stretch anyway. So that's 15/4, and then 15/4 times a half is 15/8. And then we've got, let's see, that's a 4th minus 1 is -3/4 times -1/2 is plus 3/8. So that's equal to 18/8 or 9/4 or 2.25. Okay, that wasn't too bad. And there's arc length. Let's take a look at area of a surface of revolution. Let's take a look at area of a surface of revolution. So again, let's start by understanding the geometry. Let's suppose I took some curve. And I rotated it around an axis. It doesn't have to be one of your standard axes. It doesn't have to be around X or Y. It can be around a line or whatever. But for now, for the sake of simplicity, let's say we rotated around the x-axis. So I guess this thing would form, if I can draw it correctly, this thing would form what looks to be a megaphone or maybe a trumpet, or well, not a full trumpet, but part of a trumpet. Okay, so this trumpet thing, or bugle or horn or whatever you want to call it, you could say it's composed of a bunch of layered rings. A bunch of layered rings. You could say it's made of a bunch of strips that look something like this if I draw them separately. So, how do I even draw this? Let me think. Well, I'll draw one circle that way, and how do I want to draw my other circle? So I guess what I would want to do is, yeah, draw something like that. So yeah, you've got a bunch of rings / strips of, what would I even call them? Just little ring-shaped slices of this 3D object. So whatever the surface area of these strips are, those are going to be a part of the total surface area of this rotated shape. So if I were to grab some scissors and cut through one of these strips, assuming that these strips are super thin, so this right here, their thickness is delta x, but in the limit where delta x approaches 0, they would be super thin, and that thickness, I guess you could call it, would become dx. In that case, the change in y between those 2 points where the strip starts and where it ends is going to be negligible. It's going to be relatively small, so kind of like what we did with cylindrical shells last time. Kind of the same logic applies here, where it doesn't matter which radius you use because both radii will be approximately the same. Whether you use the radius of this ring that goes to, I guess, the wider part of the strip, so this radius, I'll just call it r big, versus, that's not how you spell big, versus if your radius goes to this other part, and let's say that's the smaller part, r small, doesn't matter. R big and r small will approximately be the same. You can treat each of these rings as having an approximately fixed radius. In that case, if you cut along that dotted line and open up this strip, then here's what it's going to look like. And again, I'll just uncurl it in steps like I did with the cylindrical shell illustration last time. So we've cut it, we're starting to unfold it, and of course once you finish unfolding it, it should look like just a straight rectangular strip like that. Okay, so originally this would have been 2 pi r. So this right here is also 2 pi r, which means once you finish unwinding it, this whole thing becomes 2 pi r. Okay, so that's basically the width of this rectangular strip. And then as for the height, well, that was just the distance from here to here, which we define as being dx whenever the strips are sufficiently thin. Okay, so a small piece of area then, dA, a small slice of area for one ring, is equal to 2 pi r times dx. Or dy if we were rotating around the y-axis, but you know, same idea. Some textbooks will call it ds, capital S for surface area, so if you see that, don't be too thrown off by it. It's the same thing. And yeah, there you go. There's your formula. Wait, that doesn't look right. That doesn't look right at all. No, it's not dx. It is not dx. It's not the change in x. No. It's this right here. It's times this, which is ds. Okay, glad I caught that in time. Okay, it's not dx, it's ds. Yeah, this is ds. Yeah, because this right here is going to depend on the length of the curved segment that this ring is cut from. Okay, it's ds, not dx. That was a close call, but otherwise everything else still holds. Okay, and the ds we've already defined previously. ds is either defined in terms of dx or dy. ds is the square root of dx squared plus dy squared, which you can convert into, let's see, into one of those two forms. So yeah, depending on which way you're integrating, it's going to be this or this. But yeah, that's all there is to it. So if you understand that geometry, then you should be able to set up these problems pretty easily. Let's do a quick example or two, and then I guess we would want to move on to series after this. That's probably the big one that most students are worried about. So it says, find the exact area of the surface obtained by rotating the curve about the x-axis for this set of problems. And then another set is for rotation around the y-axis. And yeah, that's pretty much it. They're just throwing a bunch of formulas at us and asking us to integrate. So, oops, almost dropped it. So we've got, let's do y equals x cubed from 0 to 2. X going from 0 to 2. And again, this is rotated around the x-axis. So in that case, if we're rotating around the x-axis, then I would want my ds to be what? I would want my ds to be square root of 1 plus dy dx squared dx. So it's going to be 2 pi r times the square root of 1 plus dy dx squared dx from 0 to 2. Alright, so what is my radius going to be? The radius is going to be proportional to the distance between the axis of rotation. Well, it's not going to be proportional, it's going to be equal to the distance from the axis of rotation to the curve at that point. So f of x or g of y, depending on whether you're rotating around the x-axis or y-axis. So in this case, the distance is going to be f of x, so that's r. So integral from 0 to 2, factor out the 2 pi, and then r is just going to be f of x, which is x cubed, times the square root of 1 plus dy dx squared. dy dx is going to be 3x squared. dy dx here is going to be 3x squared, and the square of that is 9x to the 4th. And we can solve this pretty easily via u substitution. If that weren't the case, then maybe we would have tried trig substitution or some other technique. So we've got 2 pi integral from 0, well, I should say from x equals 0 to x equals 2 of, what's this going to be? So if I use u equals 1 plus 9x to the 4th, then du is going to become 4 times 9 is 36x cubed dx. To get 36x cubed, I would multiply by 36 over 36 here. 36x cubed dx, overshot that, is going to become my du, and then square root of u. So integral of u to the 1/2 du, and then we've got a 1 over 36, which I'll just have on the outside here. Okay, and integral of u to the half is u to the 3/2 over 3/2, which is the same thing as u to the 3/2 times 2/3. So we've got 2 pi over 36 reduces to pi over 18. Integral from x equals 0 to x equals 2. I say x equals because we're changing our variables here. I want to make sure we don't accidentally plug in 0 and 2 for u, in case you were wondering why I'm doing that. So 0 to 2, and then it's u to the 3/2 times 2/3. So 2/3, and then u to the 3/2. Oh, wait, then I don't need, so it's 2/3 u to the 3/2 evaluated from x equals 0 to x equals 2. Okay, and then rewrite the u as 1 plus 9x to the 4th. I guess I can fit that all down here. So we get pi over 18, and I might as well take the 2/3 with it. So 2 over 18 is 9, and, well, 2 and 18 reduced to 1 and 9, and then 9 times 3 is 27. So it looks like we've got pi over 27, and then 1 plus 9x to the 4th evaluated from 0 to 2, which equals pi over 27 times 1 plus, oh, wait, 1 plus 9x to the 4th to the 3/2. To the 3/2. So that's going to be 1 plus 9 times 2 to the 4th, so that's 16. To the 3/2, let me do that in a different color. Minus 1 plus 9 times 0 to the 3/2, which is just 1 to the 3/2, which is just 1. Okay, that wasn't too bad. And then, yeah, without a calculator, good luck dealing with that. 9 times 16 is 144, plus 1 is 145, and if it was just 144, it would have been simple, but square root of 145 is not something you can simplify. So that's either going to be a calculator problem or you just stop there. All right, that was one surface area problem. Should we look at another? Well, this one's marked in red, so supposedly it's going to be extra challenging. Let's give it a whirl. And this one is also rotated around the x-axis. So it says x equals 1/3 y squared plus 2 to the 3/2, and then y goes from 1 to 2. Even though it's rotated around the x-axis. Interesting. So if it's rotated around the x-axis, of course we would have to write y in terms of x. So it looks like we would have to multiply by 3, and then I guess square both sides. Okay, so we've got 3x equals y squared plus 2 to the 3/2. That's the same as y squared plus 2 cubed, all under the square root. Square both sides, and we get 9x squared equals y squared plus 2 all cubed. Take the cube root and subtract 2, and then take the square root. Oh my goodness. So we've got cube root of 9x squared equals y squared plus 2. Subtract the 2. And that gives us y squared, and take the square root. Okay, I think what I want to do before square rooting is write that as 9 to the 1/3 times x to the 2/3 minus 2 equals y squared, and then I'll say y is equal to, let's see if I take, well, I guess just that whole expression to the 1/2. So 9 to the 1/3 x to the 2/3 minus 2 all to the 1/2. Okay. That's as simple as it gets. And then to get our arc length, and we're going from y equals 1 to y equals 2, which is equivalent to x going from where to where. When y is 1, we've got 1 squared plus 2 is 3. And then 1/3 of 3 to the 3/2. Let's see, so 3 cubed is 27, and I guess that's square root of 27, and then times 1/3. 1/3 times the square root of 27. Well, that's the same as 1/3 times square root of 27 is 3 root 3. Okay, so it looks like that's just going to simplify to root 3. And then when y equals 2, we get 2 squared is 4, plus 2 is 6. So in that case, 6 cubed is 216. 1/3 of the square root of 216. Well, 216 is the same as 36 times 6. So square root of 36, that's going to be 6. So 1/3 times 6 times square root of 6. 6 over 3 is 2, so that's just 2 root 6. Okay. I guess that's really the main challenge of this problem. Once you've got that taken care of, I don't think it'll be too hard to set up your integral. Let's see what we've got. So it's the integral from root 3 to 2 root 6 of 2 pi r ds. If we're rotating around the x-axis, then r is your distance from the x-axis, therefore it's equal to y, therefore it's this. So 2 pi and then y, which is all that stuff. I'm just going to write that as cube root of 9. I'm going to keep that written as x to the 2/3 minus 2, all under the square root. So that's y, and then times the square root of 1 plus dy dx squared, which is going to be a nightmare to differentiate, but it's doable, and then times dx. Dy dx, let's see. So it's going to be, dy dx is going to be 1/2 times 1 over that stuff, or the square root of that stuff, I should say, square root of cube root of 9 times x to the 2/3 minus 2 times the derivative of this stuff, which is, oh my goodness, which is going to be, so we've got 2/3 cube root of 9 times x to the negative 1/3 and yeah, I guess that's it, times x to the negative 1/3, and x to the negative 1/3 can also be rewritten as 1 over x to the 1/3. Is there any sort of simplification that can be done here? Well, I mean, there's, not that it's worth much, but those 2's cancel out. Okay, and then we're supposed to take the square of this. So if we square it, I don't even know if the rest of this problem is worth doing. It's gotten a bit too esoteric. I can see now why it was marked in red. Unless there's some sort of shortcut that I'm missing. It's possible that I could be missing some sort of shortcut. Or maybe, was writing the 9 even a good idea in the first place? What if I wrote it as 3 squared? If I wrote it as 3 squared, then cube root of 9 would be 3 to the 2/3. 3 to the 2/3 times x to the 2/3 would be 3x all to the 2/3. Yeah, it would be easier to express it that way. Let me think on this a bit. There's got to be some sort of simplifying we could do that makes this a little bit more tolerable. Well, let's see. So we've got, I'll at least try what I just said, rewriting the 9 back as a 3. So we've got 1/3, and then you've got 3 to the 2/3 and x to the negative 1/3. I'll write x to the okay, I think I'm seeing something. I'll write x to the negative, well, it's going to be x to the just 1/3 if I move it to the denominator, and then times the square root of, that's just going to become 3x all to the 2/3 minus 2. Okay, and 3 to the 2/3 over 3, what does that become? So 3 is the same as 3 to the 1, which is 3 to the 3/3. 3 to the 2/3 over 3 to the 3/3 is 3 to the 1/3 in the denominator. So that gives us, and I guess I'll have to continue this on another sheet. So that gives us 1 over 3 to the 1/3 times x to the 1/3 is 3x to the 1/3 times the square root of, that's going to be 3x to the 2/3 minus 2. Okay, let's go ahead and take dy dx squared. So that was dy dx. What happens if we square it? Dy dx squared. Dy dx squared is going to be 1 over 3x to the 1/3. When you square it, becomes 3x to the 2/3. When you square the square root, you're just left with 3x to the 2/3 minus 2. Is it worth it to distribute here? I think it just might be. So we would get 1 over 3x to the 2/3 times 3x to the 2/3 is going to be 3x to the 4/3. Minus 2 times 3x to the 2/3. Okay, and if I put that into my integral over here, so that's 1 plus 1 over that whole messy expression. 3x to the 4/3 minus 2 times 3x to the 2/3. What does that do for us? Well, since both of these are in a square root, I can multiply this. I can distribute the insides of this square root across the insides of that one. And what does that do for me? Let's try and write that out. So I would get my main integral becomes 2 pi integral from root 3 to 2 root 6 let's see, so that can be rewritten as 3x all to the 2/3 minus 2. And if I do that, then putting this all into a single square root, what do I have? So if I'll distribute it over the 1, and that will give us 3x to the 2/3. Whoops, no, that's not right. Close the parentheses there. 3x all to the 2/3 minus 2. So that's when you multiply it by 1, plus, if I just move that, if I make a copy of that same thing, so 3x to the 2/3 minus 2, put it in the numerator of that fraction. And judging by the looks of it, I don't think yeah, I shouldn't have distributed. Okay, so I'll write it as what it originally was, which was this. So that's going to be 3x to the 2/3 times 3x to the 2/3 minus 2. And if I do that, then everything in this numerator, oh, and don't forget your dx And so now I can cancel this with this. Okay, so it's starting to shape up a bit. It's starting to shape up. And so we get 2 pi integral from root 3 to 2 root 6 of the square root of 3x to the 2/3 minus 2 plus 1 over 3x to the 2/3 dx. Where can we go from here? Where can we go from here? Well, it looks like we've got... I kind of see a quadratic in this. Yeah. Okay, yeah, I think I see it. I think I see it. I see a perfect square in there. I see it, I see it, I see it. At least I think I do. This is reminding me of a problem we did earlier. This is reminding me of, yeah, this one with the y cubed and 1 over y cubed business. That's what it's reminding me of when I see that minus 2. So let's see, how would I go about doing this? So that's a square because really it's 3x to the 1/3 squared is another way you could write it. And that's 1 over 3x to the 1/3 squared. And yeah, I think, let me test it out. So I guess complete the square would be the standard approach to do it, but I'm just going to try eyeballing it. Well, no, let's do this. So let's say, let's call it z. Let's say z is equal to 3x to the 1/3. Then in that case, all this square root business, all the business under the square root, can be rewritten as z squared minus 2 plus z to the negative 2, or plus 1 over z squared. Okay, so then in that case, I could factor this as z plus 1 over z, or no, z minus, it should be z minus 1 over z all squared. Yeah, that looks right. Okay, so I guess I didn't quite follow the steps for completing the square after all, but hopefully you can see why if I FOIL this, I get this expression. Okay, so this whole square root business simplifies to the square root of z minus 1 over z squared, which is just z minus 1 over z, which is 3x to the 1/3 minus 1 over 3x to the 1/3 dx, and now we have something that's easier to integrate. My oh my, this is one messy problem. I would imagine a problem like this, if it showed up on the AP exam, they would ask you to set up but do not solve. But, you know, it's still worth it for the mental exercise part of it, at least. It's good to flex those brain muscles. Or I guess technically we would call it flexing neurons and synapses. Yeah, maybe. I'm going to need to review my neuroscientific terminology after this. Oh, who am I kidding? I'm probably not going to do it. Anyway, so now this is easy enough to integrate. I would do a simple u substitution. U equals 3x, du equals 3dx. So you'd multiply by 3 over 3, which basically turns your 2 pi into 2 pi over 3. And the rest is pretty simple from there. So we would have 2 pi over 3 times, let's see, something to the 1/3 becomes something to the 2/3 over 2/3, or times 3/2 in other words. So that's 3/2, 3x to the 2/3 minus, let's see, so that's 3x to the negative 1/3 becomes 3x to the positive 2. Wait, that doesn't seem, oh, okay, so 3x to the 1/3, that becomes 4/3, and that's 3 over 4. Okay, that resolves it. And then this one is 3/2, 3x to the 2/3. And then that's evaluated from root 3 to 2 root 6. Have fun plugging in those numbers. I don't think I want to do anything more with this problem beyond this point. Or should I? Oh, fine. So the 3, this 3 on the outside cancels out with those 3's. And then I guess the 2 over here cancels this 2 and reduces this to a 2. And so we have pi on the outside, and then that's going to be a 1/2. And then 3 times 2 root 6. So that's 6 root 6 to the 4/3. 6 root 6 to the 4/3. Minus, whoops, why did I write an equal sign? Minus, I guess that's going to be, again, 6 root 6, but to the 2/3. 6 root 6 to the 2/3. And then we've got minus 1/2. Let's see, 3 times root 3. So that's 3 root 3 to the 4/3 minus, well, actually that's going to become a plus. Yeah, that's going to become a plus 3 root 3 to the 2/3. Okay, and if I carry on, then what do I get? I'm going to get, well, so all of these are cube roots. The cube root of 6 root 6 is root 6. The cube root of 3 root 3 is root 3. Because 3 root 3 is the same as root 3 times root 3 times root 3, and same logic goes for 6 root 6. So, okay, so we've got root 6 to the 4th power. So that's root 6 times root 6 is 6, and then times another 2 of them, so that's 6 times 6 is 36. So we've got pi times 1/2 of 36 minus root 6 squared is what that's going to become, so that's just 6. and then we've got minus 1/2, let's see, 3 root 3, its cube root is root 3 to the 4th power. That's going to be 3 squared is 9, minus, that's going to be root 3 squared, which is 3. Oh, plus, not minus. Okay. -6 plus 3 is -3. And then half of 36 is 18. So 18 minus 3 is 15. And then 15 minus half of 9. So 15 minus 4.5 is 10.5. So it looks like we ultimately get 10.5 pi, 10.5 pi. Okay, that was a fun problem. Let's move on to series. Let's move on to series before we wrap up the stream, and then tomorrow will definitely be physics. And since tomorrow's a long day, will I be able to reach electricity and magnetism tomorrow? Probably not. I'm thinking tomorrow will be focused on mechanics, both algebra-based and calculus-based, and then we'll do physics C, electricity and magnetism probably on Saturday. And then that'll be it. Anyway, let's go ahead and find my set of series examples. So I'm just going to go over the different tests for convergent and divergent series. And maybe if we have time, we'll look at a Taylor series problem or two. Just got a rather important text. I'll have to address it later, but it's not like there's much time left for this stream anyway, because I have to see someone soon enough. Where was I? Oh, right. So let's take a look at a couple of these exercises for just identifying which test you should use when looking at some random series to test it for convergence or divergence. All right, so let's have a look at something like, say we have this. Sum from, it looks like n equals 1 to infinity of, it says 2n plus 1 to the n over n to the 2n. Okay, I see something like this, and my immediate thought is that it probably is going to it's probably going to diverge, because when I look at this, I kind of see, if you ignore the n in the exponent, I see 2n plus 1 over n squared, which is effectively on the order of 1 over n. So I expect this to diverge. But how would we go about testing this? So in AP Calculus, it looks like they don't cover what's known as the root test, but the root test would actually be the quickest way to test this thing. But without the root test, you're still going to be fine, because the ratio test also works. So I would do the ratio test for this. Anytime you've got nth powers and it's not a simple geometric series, I would go for the ratio test. So let's see. Limit as n goes to infinity of, it's a sub n plus 1 over a sub n. So in other words, a sub n plus 1 times the reciprocal of a sub n. a sub n plus 1 is going to be 2n plus 1 to the n plus 1 over n plus 1 to the 2n plus 1 divided by a sub n, or times 1 over a sub n. That's going to be times the reciprocal of what we originally had. Okay, let's see what we can do here. So this series will diverge if this limit turns out to be greater than 1. It will converge if it's less than 1. Wait, is that right? Diverges if greater than 1. Converges if less. Okay, I had a little technical hiccup there, but we should be reconnected now. So, as I was saying, this limit, as n approaches infinity, if it's less than 1, then we're going to get a convergent series. If greater than 1, it's divergent, and if it's equal to 1, we need to use a different test because we can't tell either way. So let's see what we can do to simplify here. So first of all, this 2n plus 1 I can write as, well, if I distribute the 2, it's going to become 2n plus 2. So I've got limit as n goes to infinity of, and I guess I might as well distribute this stuff. Well, should I? Yeah, might as well. So distributing the 2's, I will get, that's going to become 2n plus 2, and then plus 1, so that's 2n plus 3 to the n plus 1. I'm going to write that as 2n plus 3 to the n times 2n plus 3 to the 1 over, let's see, n plus 1 to the 2n plus 2. I'm going to write that as n plus 1 to the 2n times n plus 1 to the 2. Okay, and that times n to the 2n over 2n plus 1 to the n. So out of this, I can group together the following. I can take my n to the 2n, group it together with this, and 2n plus 1 to the n, group it together with this. And if I do that, then I end up with, I guess I'll do this in orange. I end up with my limit as n approaches infinity of n to the 2n over n plus 1 to the 2n. I can just write that as n over n plus 1 all to the 2n times 2n plus 3 to the n over 2n plus 1 to the n. I can write that as 2n plus 3 over 2n plus 1 all to the n. And then times, we're left with a single 2n plus 3 over an n plus 1 squared. Okay, and the limit laws say that I can take the limits one part at a time. So I can take the limit of this thing separately from this thing, separately from this thing. Okay, as n approaches infinity, n over n plus 1 approaches 1. So this is going to approach 1 to the 2n. I mean, technically you would have to use L'Hopital's rule because it's 1 to the infinity, which is an indeterminate form, but I think it's fairly obvious that this is going to go to 1. 2n plus 3 over 2n plus 1, that's also going to go to 1. So this goes to 1, this goes to 1, And that leaves us with the limit as n approaches infinity of 2n plus 3 over n plus 1 squared. Okay, well, that's going to have an n squared in it, and that's going to just be linear. So 2n plus 3 over n squared plus 2n plus 1, that's just going to go to 0, which is less than 1. Therefore, this series actually converges, much to my surprise. Okay, so that series converges. How about 1 over n square root, wait, is that right? Yeah, 1 over n square root of the natural log of n. So it looks like that starts from n equals 2. It would have to, because if you start at n equals 1, natural log of 1 is 0, and dividing by 0 would create problems. 1 over n square root natural log of n. Okay, does this converge or diverge? If I see natural logarithms, then usually the best course of action is to just use the integral test. Is the integral test still included on the AP exam, or was that one of the omitted tests? Oh well, in any case, even if you don't need it for the AP exam, you are going to need it in college. So let's see, I would go for the integral test here, so I would say the integral from 2 to infinity of 1 over, let's call it x, square root of the natural log of x dx. What would that be? Well, I would have to do a u substitution, it looks like. U equals natural log of x du equals 1 over x dx. Oh, I have that. I have a 1 over x dx. It's right here. Okay, so that's a bit promising. So it becomes integral from x equals 2 to infinity of, that's going to become a du, and we're going to be left with 1 over the square root of u, which is the same as u to the negative 1/2, which integrates to u to the positive 1/2 over 1/2, so that's 2u to the 1/2, which is 2 square root of ln of x, evaluated from 2 to infinity. Not that you can actually evaluate it this way. You would have to rewrite it as the limit as, let's call it t approaches infinity of 2 square root of the natural log of x from 2 to t. And that would give us the limit as t goes to infinity of, well, I can factor out the 2. So 2 times the limit as t goes to infinity of the square root of the natural log of t minus the square root of the natural log of 2. Okay, substituting infinity for t, it just goes to infinity, so this diverges. Since the integral diverges, so does the corresponding series. Let me see. Here's one that's rather simple once you know how to deal with it. Most of you will probably think this is too simple to even consider as a worthwhile example, but let's just put it out there. So n equals 1 to infinity, the sum of, we've got 1 over n cubed plus 1 over 3 to the n. Okay, so you can actually split this up into two separate series. This is equal to the sum of 1 over n cubed plus the sum of 1 over 3 to the n. So you can test each part of this separately, and if they both converge, then that's it. Their total also converges. But if even one of them diverges, then the thing as a whole would have to diverge as well. 1 over n cubed converges by the p-series test, is what it's sometimes called. Since the exponent in the denominator is greater than 1, that's your p-series test. That tells us that this is going to converge. Technically, you should be using the integral test here, but you know, p-series test is just a shortcut for these simplified cases. And then 1 over 3 to the n, that's 1/3 to the n. That's a geometric series with the absolute value of r being equal to 1/3, which is less than 1. Therefore, it converges by the geometric series test. Both parts converge, which means their total must also converge. And there you go. That was pretty much as simple as it gets. Here's one that's rather unique, and it throws students for a loop the first time they see it. We've got the sum from 1 to infinity of, it's written as 1 times 3 times 5 times ... times 2n minus 1 over, we've got 2 times 5 times 8 times ... and that is 3n minus 1. And does this converge or diverge? So a lot of students are perplexed when they see something like this for the first time, but this shouldn't actually bother you because it's very, very similar to a factorial. It's very, very similar to a factorial. If I wanted to write n factorial, one way of writing it would be 1 times 2 times 3 times ... all the way up to n. So these aren't quite factorials, but they bear some resemblance to factorials. And when you see factorials, you want to go with the ratio test. The ratio test is pretty much the only test I've ever seen being effective on series that involve factorials. So just go with the ratio test for this. And so we take the limit as n goes to infinity of a sub n plus 1 over a sub n. In other words, a sub n plus 1 times 1 over a sub n. A sub n plus 1 is going to be 1 times 3 times 5 times all that stuff times 2n minus 1 times 2 times n plus 1 minus 1. If I distribute the 2 over the n plus 1, that's 2n plus 2 minus the 1 becomes 2n plus 1. And then we've got 2 times 5 times 8 times ... 3n minus 1, and then what's 3 times n plus 1? Well, that's 3n plus 3, and then minus 1, that's 3n plus 2. Okay, times 1 over a sub n, so I'm just going to draw a copy of this. Well, write a copy of this, but upside down. So that's 2, 5, 8, so on and so forth. until 3n minus 1, and this is 1, 3, 5, and so on until 2n minus 1. Okay, we can cancel pretty much everything, almost everything. 1, 3, 5 all the way through 2n minus 1 cancels with all that. 2, 5, 8 all the way through 3n minus 1 cancels with all that. And we're left with the limit. As n approaches infinity of 2n plus 1 over 3n plus 2, which, if you've seen this enough times, you should easily be able to determine is 2/3, which is less than 1. The ratio test tells us that if the limit is less than 1, then the series converges. Okay, so that series converges. What else should we look at as an example? Here's one. So we've got actually, do I want to do that one? Yeah, not so sure about that one. I guess, let me see, what am I looking for? I can't seem to find it here. Oh well, maybe I'll stumble upon it later. But here's one that's actually not too bad. The sum from 1 to infinity of sine of 2n over 1 plus 2 to the n. Okay, so for something like this, what I would do is something that's akin to the squeeze theorem in a way. We know that the sine function only gives us values between -1 and 1, so I can say that this series falls between and I'm going to have to squeeze this in pretty tightly, but the sum of -1 over 1 plus 2 to the n. Yeah, you can hardly even read that. And the sum of +1 over 1 plus 2 to the n. And if this converges and it's a larger series, then we can just do a direct comparison test and be able to conclude that this main series also converges. Okay, so does 1 over 1 plus 2 to the n converge? Absolutely it does, because we can just do a limit comparison test. If I take the limit as n approaches infinity of, well, let's see. I know that 1 over 2 to the n converges. I know 1 over 2 to the n converges by the geometric series test. And so if the limit of the ratio of 1 over 2 to the n and 1 over 1 plus 2 to the n, if the limit of that ratio is a constant, then that means that this series and this series are what I would call comparable. And if two series are comparable, then they share the same fate. If one converges, the other converges. If one diverges, the other diverges. Comparable is not an official term, by the way, so don't write that down on your exam. That's just the word I like to use. If a pair of series are comparable, then they do the same thing in terms of whether they converge or diverge. Anyway, limit comparison test. So one over the other, it doesn't matter which one you put on top and which one you put on the bottom. So I'm just going to put 1 over 2 to the n on top and 1 over 1 plus 2 to the n on the bottom. That's equal to the limit as n goes to infinity of, that's going to be 1 plus 2 to the n over 2 to the n, which equals the limit as n goes to infinity of 1 over 2 to the n plus 2 to the n over 2 to the n, which is 1. 1 over 2 to the n as n goes to infinity is 0, so this limit evaluates to just 1, and 1 is a constant. As long as your limit in the comparison test evaluates to a constant, then the two series that you took the ratio of in your limit are comparable. So we got a constant ratio between them. That says it all. Since this converges, and since this converges by the limit comparison test, sine of 2n over 1 plus 2 to the n would converge by the direct comparison test, since we can directly see that it's less than or equal to something that itself has a finite sum. All right, and I guess this is where we will have to stop because I have other obligations to attend to. I don't know if I'll go back to calculus at all. I don't want to neglect the physics students, so if we can clear physics, then maybe we'll go back to more calculus and do a little bit of power series, Taylor series, and all that. But if not, then I imagine you'll have gotten plenty of practice with that stuff since it's among the more recent topics, and usually it's one of those topics that students worry about the most anyway, so chances are you've already been practicing a lot with this. But yeah, that's where we will have to end it for today. For those of you who are doing AP Physics 1 or AP Physics C, I'm going to be focusing on mechanics tomorrow, so that's when I will see you. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I'll see some of you guys tomorrow.